Hello everybody, getting ready to do lesson 4.8 part 2 today of pre-calculus math. And it's applications and models, trigonometric functions. You got 10 points here that goes in your notebook, a huge amount. Have your notebook ready. Notebook guides are available from me if you need them. 55 points here will go on your classwork sheet today. And today's bell work, teachers and students. We have write the standard form of the equation of the line that passes through the specified characteristics here. So you have 2 points here. Write an equation of the line that passes through these 2 points, students. Give you about 5 minutes to do that. Okay, welcome back for your solutions for today's bell work. Then up here we find slope. We get negative 4 over 5 for a slope. And then this is our standard form of an equation of a line here with a point line, or point slope here. We got point here and a slope. And we crank this out here, y minus 2 equals negative 4 over 5 times x minus 3. And we end up with this situation here, 5y minus 10 equals negative 4x plus 12. And then we move everything over to the left-hand side here. And we come up with this for 79. Down here, we're going to find slope, which when we crank it out, you should know that by now, rise over run. Y2 minus y1, x2 minus x1, blah blah blah. You should know this since like the 6th grade, students. So this is a huge review for you, kind of like a giveaway actually, 10 points, but I still have students who can't get this, so we go over it and then we use our standard form of an equation of a line with a point and a slope. And then we crank it out here, and then we end up with 3y plus 2 equals negative 4x plus 1. Then we move everything over to the left-hand side, and we end up with this. Okay, notebook. In air navigation, bearings are measured in degrees clockwise from the north. So if you're planning to fly in anything here, like this be a kite here, motorized kite. This would be the way that you would, a diagram of this situation up here. For example, bearings are measured in degrees clockwise from the north, so this would almost be like a negative situation here. This would be north here. Then clockwise here would be 60 degrees clockwise north here. It's funny because with trig, everything goes counterclockwise, but with air navigation, things go clockwise, so you can get kind of confused that way. And then this situation here would be a 225 bearing here, 225 degrees, going clockwise, whereas in trig, again, you start here and go like that for negative and positive like that. So make sure you don't get that confused. Okay, moving into our next example here. Example 5, finding directions in terms of bearings. A ship leaves a port at noon and heads due west at 20 knots, or 20 nautical miles per hour. So we head due west here at 20 knots to here, to point B. At 2 p.m., this is 2 p.m., the ship changes course to north 54 west. So this is the change of course here, 54 west as shown. Find the ship's bearing and distance from the point of departure at 3 p.m. So it's here at 2 p.m. Started at noon here, 2 p.m. This is 3 p.m. up here. So find the ship's bearing and distance from port. So we need to know the bearing and also this distance here from the port, the direct distance there. So for triangle BCD, we have a triangle here that we form here. We can use this to analyze our distances here. BCD, you have here because we need a right angle here. So 36 and 54 would be 90. The two sides of this triangle can be determined to be b equals 20 sine 36. So b, which would be here, we need to find this distance here so we can do our problem. B equals 20 sine 36, and d, which is here, equals 20 cosine 36. So we're using a cosine function and a sine function from this angle here. So, knowing that information, we now know that the bearing of the ship is north 78.18, which is right here. That's our bearing on that. Finally, from the triangle ACD, you have sine A. So sine angle A over here is B over C, which is our hypotenuse here, B over C, which will yield C, in this case, be B over sine A. We're going to use sine A for C here. So we're substituting sine A for C because we know sine A is sine 11.82 degrees. We know our angle measure here is 0.82. So B is 20 sine 36. We know that. And then when you crank this out on your calculator, you come up with 57.39 nautical miles from the distance of the port, which would be our C, our distance here, would be that distance there. Okay, into our guided practice here. Another ship leaves the port problem, has a bearing of south 29 degrees west. The ship sails at 20 knots. How many nautical miles south and how many nautical miles west does the ship travel by 6 p.m.? So for that there, we have 90 minus 29 degrees equals 61 degrees. So 20 times 6 would be 120 nautical miles. We know the distance of that travel. And so sine 61, we know our distance here, is sine, which this would be our hypotenuse here of our triangle, A over 120. And so when we crank this out, we have A equals 120 sine 61, which comes out to 104.95 nautical miles south. so we know that much. And then our cosine would be b over 120, and b would equal 120 cosine 61, which would equal 58.18 degree nautical miles west. So using our triangle here, here's our distance, here is a here, sine 61 equals sine 61 will give us our A. We discovered our A is 104.95 for A, and then B, knowing both sides now, without using our Pythagorean theorem, we can find that B will equal 58.18 here by using our sine and cosine functions for that problem there. In your notebook, harmonic motion. The periodic nature of trig functions is useful for describing the motion of a point or an object that vibrates, oscillates, rotates, or is moved by a wave motion. So, for example, consider a ball that is bobbing up and down on the end of a spring. This is your visual here for that. Suppose that 10 meters is the maximum distance the ball travels upward or downward from its equilibrium at rest position. So suppose, this 10 centimeters here, then this would be down here to what they call negative 10. So you have a total distance here of 20. And then this would be up here when it retracts. It would be back up here to the 10 centimeter mark here. And they call that equilibrium negative displacement and positive displacement. Okay, so suppose further that the time it takes for the ball to move from its maximum displacement above 0 to its maximum displacement below 0 and back again is 4 seconds. So now time situation on that. Assuming the ideal conditions of perfect elasticity and no friction or air resistance, the ball would continue to move up and down in a uniform and regular manner. From this spring, you can conclude that the period, time for one complete cycle of the motion, is period equals 4 seconds. Its amplitude, maximum displacement from equilibrium, is 10 centimeters. So maximum displacement from equilibrium will be 10 centimeters. And its frequency, number of cycles per second, is frequency would equal 1 over 4 cycles per second. Got some stats there on that phenomenon. Motion of this nature can be described by a sine and cosine function and is called simple harmonic motion. Definition of simple harmonic motion. A point that moves on a coordinate line is said to be in simple harmonic motion when its distance d from the origin at time t is given by either d equals a sine wt or d equals a cosine wt, where a and w are real numbers such that w is greater than 0. The motion has amplitude a, absolute value of a, period is 2 pi over w, and frequency is w over 2 pi. So we got some facts there laid down. Example 6, simple harmonic motion. Write the equation for simple harmonic motion of the ball illustrated here. And we got a situation here, again with the same extensions here, with the ball on the spring, where the period is 4 seconds. What is the frequency of this motion? So because the spring is at equilibrium at t equals 0, which would be here, when t equals 0, so this is where it rests, d would equal a sine wt. So our distance here would be d equals a sine wt. Moreover, because maximum displacement from 0 is 10 and the period is 4, you have the following. Amplitude equals 10. So our absolute value of a would equal 10. This will be our amplitude here, from here to up here, and then from up here to down there. So our net amplitude would be a distance of 10 units for that. So knowing that period would equal 2 pi over w equals 4, we know this value here, we know 2 pi. So to find w would equal pi over 2. So consequently, the equation of motion is d equals 10 sine pi over 2t. Note that the choice of a equals 10 or a equals negative 10 depends on whether the ball initially moves up or down. The frequency is w over 2 pi, and then in this case here, pi over 2 is our w. We've established that up here. Pi over 2 equals w. Pi over 2 over 2 pi, which would equal to 1/4 cycle per second. So by plugging these values into our formula, it corresponds to 1/4 cycle per second. Let's try guided practice now. Find a model for simple harmonic motion satisfying the specific conditions. So displacement when time equals 0 is 0, displacement amplitude is 8, and then our period is 2 seconds. So knowing that, d equals 0 when t equals 0, or a equals 8. So a equals 8 and period equals 2. So we've established that. So use d equals a sine wt. Since d equals 0 and t equals 0, period would equal 2 pi over w equals 2. Therefore, w would equal pi in this case here. So our period would equal pi, and then thus d equals 8 sine pi t would be the formula for that harmonic motion. One illustration of the relationship between sine waves and harmonic motion is wave motion that results when a stone is dropped into a calm pool of water. The waves move outward in roughly the shape of a sine or cosine. So this would be kind of a visual here of a wave motion. As an example, suppose you're fishing and your fishing bob is attached so that it does not move horizontally. As the waves move outward from the dropped stone, your fishing bob will move up and down in a simple harmonic motion. So again, another problem in simple harmonic motion. Given the equation of simple harmonic motion, d equals 6 cosine 3 pi over 4t, find a, the maximum displacement, b, the frequency, and c, the value of d when t equals 4. So, and also d, the least positive value of t for which d equals 0. Given the equation as a form, d equals a cosine wt with a equals 6, our a is here at 6, and w equals 3 pi over 4, here's our w here. A, the maximum displacement from the point of equilibrium is given by the amplitude, so the maximum displacement will be 6. This is our resting distance. And then the frequency would equal w over 2 pi, which would equal our w we established as 3 pi over 4 over 2 pi. Then when we crank that out, we get 3 over 8 cycles per unit of time. And then c would be d equals 6 cosine 3 pi over 4 multiplied by 4, which would come out to 6 cosine 3 pi, which would equal 6 times negative 1. 3 pi would be negative 1. So it would be negative 6 for d. d would equal negative 6. And then to find the least positive value of t for which d equals 0. So solve the equation. D equals 6 cosine 3 pi over t, 3 pi over 4t equals 0. First divide each side by 6 to obtain cosine 3 pi over 4t equals 0. You know that cosine t equals 0 when t equals pi over 2, 3 pi over 2, 5 pi over 2. Multiply these values by 4 over 3 pi to obtain t would equal 2/3, 2 and 10/3. So the least positive value of t is t equals 2/3. This will be your least positive value here for these set of values here. The maximum displacement from the point of equilibrium, d, would equal 6. So this would be our amplitude here would be 6. d cosine 3 pi over 4t. This would be a graph of that function. And then the period is the time for the graph to complete one cycle, which in this case here, from this max to this max, would equal 2.67 down here on your time would be on your x-axis, your horizontal axis here. And then you can estimate the frequency as follows. Frequency would equal 1 over 2.67, which comes out to 0.37 cycles per unit of time. So that would be right there. The value of d when t equals 4 is d would equal -6 when the value of d would equal 4 here, or when t equals 4, I'm sorry. So when t equals 4, d would equal -6. That would be the position of the object. Then over here, the least positive value of t for which d equals 0 would be right here. Would be the least positive value would be t would equal 0.67 or 2/3. So that's where we got that graphically, and we did that trigonometrically earlier. So going into our next problem here on your classwork sheet, simple harmonic motion described by the trigonometric function. Find a, maximum displacement, b, frequency, the value of d when t equals 5, and d, the least positive value of t for which d equals 0. Use a graphing calculator to verify your results. So here's our function here. Maximum displacement would equal amplitude would be 4. Frequency would be w over 2 pi. In this case here, be 8 pi over 2 pi. So 4 cycles per unit of time. And then c, t equals 5. d would equal 4 cosine 8 pi 5, which would equal 4 here. And then d, last positive value of t for which d equals 0, and we plug in our values to find that last positive value, and we get down to 1 over 16 for that.